Okay, so in this video I'm going to talk about some examples related to diagonalization. So we are going to have some examples, and let's see how we are going to understand more what we have explained last time. Okay, now let's jump directly to this example and see whether that it is going to be working with us or not. First of all, we assume that we have a matrix, okay, called A, and this matrix we are going to have these values for it, which is -1, 4, 0, and 3. And A has eigenvalues. These are the eigenvalues, okay, -1 and 3. And I think that you understand what is the meaning of eigenvalues according to what we have explained before. And corresponding linearly independent vectors. Again, these words are significant. Each one is significant. So they are linearly independent. It means that we are having like distinct eigenvalues for them. As you can see, we have distinct eigenvalues. Okay, so this means that we are having linearly independent vectors. And I mentioned what is the meaning of independency regarding the eigenvectors before. Okay, so now the independent eigenvectors that we have are 1 and 0 and 1 and 1. These are the two eigenvectors that we are having. Okay, then we are going to form P, which is the matrix that is going to be formed from the eigenvectors or the independent eigenvectors that we have for this system or for this matrix. Okay, so we're going to put them as columns here, 1 and 0 and 1 and 1. So we are going to put them as they are in the same sequence. So let me clear here. So take care that we are putting them in the same sequence. 1 0, so it is 1 0 here. 1 1, it is 1 1 here. Why? Because this -1 is associated with this eigenvector, and this 3 is associated with this eigenvector. Okay, so take care of the sequence of the eigenvectors, okay, and the corresponding eigenvalues. Okay, now we're going to determine P minus 1. P minus 1. Okay, remember that we are dealing, or we are searching for what we call it P minus 1, which is the inverse times A times P. This is what we are trying to get, right? This is what we are going, or what we are trying to get. So we formed first P, which is the matrix that is going to be used for diagonalization of A, and then we are going to obtain this product that we are going to have, okay, and after that this product is going to have the eigenvalues across or down its diagonal. So P minus 1 is going to be, try to get P minus 1 the inverse of P. It's very easy for you, 4 elements only matrix, then you can obtain P minus 1 easily, right? So check it, and you're going to obtain it to be like this: 1 0 minus 1 and 1. Okay, now let's go to the next part. Okay, so here a simple computation shows that P minus 1 A P, or the inverse of P times A, or dot A dot P, equals to -1 0 0 3. Okay, we are going to put P minus 1 as we have obtained it, okay, from the previous slide. Okay, let's clear. So this is P minus 1, this is A, and this is P. So if you are going to dot product, or you are going to multiply these matrices together, then you are going to obtain this matrix. Okay, so what is this matrix is? It is a diagonal matrix with the eigenvalues of A on the main diagonal, right? So we have -1 and we have 3 here, right? And the off diagonals, they are zeros, right? So this diagonal, it contains this order, in this order. So we are having -1 and we are having 3. These are the eigenvalues, right? So this is what we are trying to find. Actually, we have given this in the beginning, but actually we want to show to you that if we have these eigenvalues and we could form p minus 1 a p, okay, so if we have the eigenvectors and we form this p minus 1 a p, then we can obtain this eigenvalues easily at the diagonal of this multiplication. Okay, and this is what we are going to obtain at the end. This is what we are going to obtain at the end. So we're going to obtain a diagonal matrix, as you can see, with eigenvalues on the main diagonal, as you can see it here, in the order in which the eigenvectors were used to form the columns, right? Because -1 as it -1, it is related to what? To the first eigen. This is the first eigenvector. And then 3, which is the second one here, it is related to the second eigenvector. Okay. If we reverse the order, look here, if we reverse the order of these eigenvectors as columns and define, so we are going to define, let's assume that we are going to define Q instead of P, and say that instead of having P 0, 1, 0, 1, 1, it is going to be 1, 1, 1, 0. So we flipped the eigenvectors. Then if you are going to make the multiplication, which is Q minus 1a Q, it will give you exactly the flipped eigenvalues. So we're going to have 3 minus 1. So the 3 is corresponding to this eigenvector. This minus 1 is corresponding to this eigenvector. Okay? With the eigenvalues along the main diagonal, but now in the order reflecting the order of the eigenvectors used in forming the columns of Q. As we have said that before. Do you remember that I have mentioned about this before in the theorem? Let's recall theorem 9.6, which is in the next slide. This part. Do you remember this part that I have explained 2 or 3 videos before? If Q is any matrix that diagonalizes A, then necessarily the diagonal matrix Q minus 1 A Q has the eigenvalues of A along its main diagonal. And look here, the columns of Q must be eigenvectors of A. And this is the most important part here, the key, which is in the order in which the eigenvalues appear on the main diagonal of Q minus 1 A Q. Okay, that's the key word here, in the order. Okay, so if we go back, this is the order here. First eigenvector with eigenvalue, second eigenvector with the second eigenvalue. Okay? Okay, so now this is first example. Now let's go to the next example and see how we can solve it. It's a little bit like higher, the dimensions of the matrix is going to be higher here. Let A equal to this matrix, minus 1, 1, 3, 2, 1, 4, 1, 0, minus 2. Okay, let's assume that the eigenvalues, okay, this is given, like a given for us in order to check later what we are going to have. Okay, so the eigenvalues are minus 1, and the second is minus 1 plus radical of 29 over 2, and the last eigenvalue is minus 1 minus radical of 29 over 2. Okay, and the corresponding eigenvectors, so we have the eigenvalues and we have the eigenvectors here. Okay, just we are going to see that what we have explained in our theorem is working well with us. So the eigenvectors are going to be like 1 minus 3, 1, and 3 plus the radical of 29, 10 plus 2 the radical of 29, and 2. And here the last eigenvector, the difference is going to be in the signs here. It is positive, positive here, it is negative, negative, and the remaining are the same. So if I ask you, are these eigenvectors linearly independent or not? Linearly independent or not? The answer is what Yes, they are linearly independent. Why? Because from the beginning I told you that eigenvalues are, as you can see here, these are the eigenvalues. They are distinct. They are different, right? This necessitates that the eigenvectors, corresponding eigenvectors, they are different and linearly independent. Okay, so we cannot have multiplication of one vector of the other, for example. So these are linearly independent. Okay, that's very important, linearly independent, because the eigenvalues are distinct, as I have mentioned here. Use these eigenvectors as column of P to form. We want what? At the end, we want to form this P minus 1AP, right? To get the eigenvalues down its diagonal. Even that we know the eigenvalues, but we are going to check this. We are going to check that what we have said in our theorem is okay, working well. Okay, so we're going to form P, as you can see, P here. P, it is the first eigenvector, the second eigenvector, and the third eigenvector, as you can see it here. Okay, so we have formed P from the eigenvectors available for us, right? Okay, now let's go. We find that P minus 1, then we are going to obtain the inverse of P. We have P, so we are going to obtain the inverse of P. P minus 1, please, you can check it by yourself also, and you can make it as a little exercise for you to obtain the inverse. Do you remember how to obtain the inverse of the matrix? Please revise the previous videos to get what I am telling you, or how the inverse can be obtained easily. Okay? Then after making it, please make this exercise, and you are going to find by one way or another that this is the inverse. The radical of 29 over 812 times these values, as you can see here. Then make the multiplication P minus 1AP. Okay, P minus 1AP. You're going to find that the multiplication would yield on the diagonal values. These three values are going to be the eigenvalues, and the off diagonal, as you can see here, they are zeros, right? So this is the first eigenvalue, lambda 1, for example. This is the second, lambda 2, and this is lambda 3, for example. So we have the diagonal is giving us the eigenvalues, right? Okay, and in this case we are having the corresponding eigenvectors related to these eigenvalues. So we have three linearly independent eigenvectors related to three distinct eigenvalues. Okay, so what we are going to have here, okay, with the eigenvalues down the main diagonal, as we said. So this matrix that is composed of this multiplication, we are going to have the eigenvalues down its main diagonal in the order of the eigenvalues listed for the columns of P, right? If we go back here, where is B? This is P, first eigenvector, second and third. So we have lambda 1 related to this, lambda 2 related to this, lambda 3 related to this one. Okay. So now in this example, P minus 1 is an unpleasant matrix. That's right, look here, a lot of, it's a lot of calculation, and we need to calculate even P minus 1 AP and so on. But actually, no need to multiply and no need to make all of this. Just we are giving you the eigenvectors here. We're giving you the eigenvalues and giving you the eigenvectors in order to be sure that P minus 1 AP is going to give us the eigenvalues along its diagonal. This is what we are trying to verify here, right? So in this case, you're going to find the forming P1 is a little bit time consuming, and it's not pleasant at all also. But no need to make this, because at the end you can form P minus 1 AP, for example, from the eigenvalues that you have obtained, if you are interested to obtain this matrix. So we have the eigenvalues, put them along the diagonal, put zeros on the off diagonal, and that's it. That's done for you. Now you can obtain this. In this example, P minus 1 is an unpleasant matrix. One of the values of theorem 9.6 is that it tells us what P minus 1 AP P looks like. That's right, as we have mentioned here, without actually having to determine P minus 1 or the inverse and carry out this product. So just we are going to say, if we have, for example, the matrix A, we have the eigenvalues and the eigenvectors, then without making any interruption or making any problem or making any like calculation, we can calculate P minus 1A P simply, okay? Simply by putting the diagonals as the eigenvalues and the off diagonals to be 0. What we have done before, as I said, this is a verification of the theorem. We have everything here, okay? The eigenvalues and the eigenvectors. So we are like verifying the theorem, verifying that really P minus 1 AP is going to give us the eigenvalues on the diagonal, down the diagonal, right? But again, the theorem that we have explained before, the theorem 9.6, it tells us the relation between the matrix A and the diagonalizing matrix P and the form of the matrix P1A P minus 1A P. Okay, I hope that you have understood this. Maybe next time I'm going to also give some couple of 2 examples, and I hope that it works well with you to understand diagonalization in a good way. Thank you, and see you in the next video.